All right, so now what we're going to do is we are going to start graphing exponential functions, and then we are going to transform them, and then the next day we're going to kind of relate this to logarithmic functions. So, graphing exponential functions. What makes something an exponential function? Well, think about the word exponential function. What makes something exponential? Well, the variable is in the exponent. Okay, we're going to talk a little bit more about what this means after, so we're just going to leave it. But we're going to start by graphing a base exponential function. We are going to graph y equals 2 to the x. Now we're going to do this simply by using a table of values the first time, and then you'll kind of get used to the shape. But if you were to graph y equals 2 to the x, what you're putting in is different values for x in the exponent. So for this first one, we have 2 to the 3, which is 8. Then we have 2 to the 2, which is 4. We have 2 to the 1, which is 2. 2 to the 0, which would be 1. Anything to the exponent 0 is 1. Then we've got 2 to the negative 1. Now, 2 to the negative 1, remember anytime you have a negative exponent, you're in the wrong place. So we're going to do it as 1 over 2 to the 1. So it's going to be 1/2, which is going to make this 2 to the negative 2. So 1 over 2 to the 2, or 1/4. And then we have 2 to the negative 3. So 1 over 2 to the 3, which would be 1 over 8. And now let's sketch it. So let's start with this middle point here at 0, 1. It's going to become an important point. And then we're going to graph when x is 1, y is 2, when x is 2, y is 4, and when x is 3, y is 8. And we're going to notice that on the right side of this graph, what's happening? Well, as my x values are increasing, my y values are also increasing. So as x increases, y increases. And where's it going? Like where is this arrow approaching? Well, it's going to infinity and beyond. All right, let's look to see what happens when x decreases. So we're going to put in a value like -1. When x is -1, y is 1/2. When x is -2, y is 1/4. When x is -3, y is 1/8. And can you picture where graph is going? As my x values are decreasing, my y values are also decreasing. So as x increases, y decreases. But where's it going towards? Think about your rational functions. What kind of behavior is this graph exhibiting? Well, it's asymptotic behavior. This graph is approaching the x-axis. So it's approaching where y is equal to 0. Will it ever get there? No, it's approaching it, right? It's an asymptotic behavior, which means that this graph must have an asymptote at y equals 0, because it's a line that my graph is approaching but never reaching. This is not asymptotic behavior. This is just at y increasing as x increases, but this is asymptotic behavior. I'm approaching this y equals 0. What's the intercept of this graph? Well, there's an intercept at 0, 1. The domain of this graph is -infinity to infinity. There's nothing I can't put in for x. And then my range is going to be y is greater than my asymptote, so greater than 0. Awesome. So now I want to do the same thing, but this time we're going to do it of y equals 1/2 x. So what's going to change? Well, let's put in my x values. So when we have 1/2 to the 3, right? So it's 1 to the 3 over 2 to the 3, or 1/2 times 1/2 times 1/2, we're going to get an eighth. When we have 1/2 to the 2, we're going to get 1/4. 1/2 to the 1, we're going to get a half. And then when we put in an exponent of 0, anything to the exponent 0 is 1. Then when we put in -1/2, it's going to flip it, right? Negative exponent says you're in the wrong place. So instead of being 1 over 2, this is going to be 2 over 1 to the 1, so I get that 2. When x is -2, again, I'm going to flip it and say this is 2 to the 2, which is 4. And then 1/2 to the -3 would be 8. So what's happening this time? Well, let's start at that same point, 0, 1. Ooh, that's something they have in common. Both of these graphs have a y-intercept at 0, 1. Now what's going to happen to my x value or my y values as my x values increase? Well, when we put in x is 1, I got a half. When I put in x is 2, I got a quarter. When I put in x is 3, I got an eighth. What is happening to this graph? As my y values are increasing, or sorry, as my x values increases, my y values decrease. And this time, where are they going? Well, they're exhibiting that asymptotic behavior again. They're approaching 0, which means I have an asymptote at y equals 0. And then what happens is my x values decrease. Well, when we put in -1, we got 2. When we put in -2, we got 4. When we put in -3, we got 8. And my y values were increasing towards infinity. As my x values decrease, my y values increase towards infinity. The domain of this graph is still -infinity to infinity. And the range is still y is greater than 0. So when you look at the bottom parts, I'm just going to shrink this down a little bit. When you look at the bottom parts of these two graphs, and we're talking about their features, the asymptote is the same, the intercept is the same, the domain is the same, and the range is the same. What's different is that this is an increasing graph. So as x increases, y increases. And with this one, we could call this a decreasing graph, or as x increases, y increases, y decreases. What else do you notice about these two graphs? Think about transformations. If you looked at these on the same grid, this graph compared to this graph, what could you say about them from a transformation point? So you've got stretching, shrinking, reflecting, left, right, up, down. If you thought about how you compare these two, which of those words would you use? Well, hopefully you notice that they are reflections of each other over the over the y-axis. So what do you notice about the graphs? They are reflections over the y-axis. Could we prove algebraically that the graph of y equals 1/2 x is just a reflection over the y-axis? Well, let's think about it. If I had a graph like y equals 2 to the x and I wanted to reflect it over the y-axis, which values would I be reflecting? X or y? It's the x. So if I think about that, if I wanted to reflect this over the y-axis, I would reflect it in the x values. So this is 2 to the -1x. Another way of writing that would be 2 to the -1x, right? -1 times x is -x. 2 to the -1 is the same as 1/2 to the x. So the graph of y equals 1/2 to the x is a reflection of the x values over the y-axis of a graph of y equals 2 to the x. So they share all the same properties of asymptotes, intercepts, domain, and range, but they are just one is an increasing graph and one is a decreasing graph. Let's look what happens when we make the bases entirely different. So let's say we want to make the base a 4 or 2.5. What's going to happen then? Well, that's these two graphs here. So y equals 4 to the x is this yellow graph. Y equals 2.5 to the x is the blue graph. And then there's also a y equals 1.8 graph. On the other graph here, we've got y equals 0.25, 0.4, and 0.7. And really what I want you to see is the difference between these graphs. Why do you think I chose these two to be on different grids? Like why is the 4 and the 2.5 and the 1.8 over here? And why is the 0.4, the 0.7, and the 0.25 over here? Well, these are a values that are between 0 and 1. And these are a values that are greater than 1. What do you notice about all of them? Well, let's look at the asymptotes of all of them. Did it change? Or is it always y equals 0? And does it make sense that it's always y is equal to 0? Well, no matter what the base is, as I make that exponent for these ones smaller and smaller, I'm still getting a fraction, right? So 4 to the -100 is still 1 over 4 to the 100. So it's a tiny number, but it's still a number greater than 0. Same thing here. If I make the number bigger and bigger, I've got this fraction to an exponent, and all that's going to happen is it's going to get to be a smaller and smaller number, but it's never going to be 0. It's going to approach 0. So no matter what I make the base, my asymptote of an exponential function will always be y equals 0. What about the domain of these graphs? What do you notice? Well, they're all -infinity to infinity. Sweet. What about the range? Well, for every single one of these graphs, we had an asymptote at y equals 0, and the graph is above the x-axis. So for every single one of these, the range is y is greater than 0. Now I realize that I've switched myself to set notation. Let's switch ourselves back to interval notation because that's what the textbook likes. So the range is 0 with a round bracket to infinity all the way through. And if you want to go back up here and change those two, I'm just such a set notation person, but I did do the domain and interval notation, and then I switched to range and set notation. I don't know. I'm amni notation, like ambidextrous. Anyway, whatever. So if you want to switch those to interval notation, they should keep to interval notation. Okay, what about increasing versus decreasing? What do you notice? These graphs are doing what? They're decreasing. We're going to call these, when we do applications, we're going to call these exponential decay graphs, where over time, the amount of what you have is decreasing. So these graphs here, where the a value is between 0 and 1, they're all decreasing graphs. So these two here are going to be decreasing graphs. Whereas the y equals 4 to the x and y equals 2.5 to the x, they are increasing graphs. Why? Because the a value is greater than 1. And then what about the y-intercept for all these graphs? Well, hopefully you can see that these all have a y-intercept at 0, 1. So the moral of the story here is that it doesn't matter what your base is. Your asymptote, domain, range, and y-intercept won't change. The only thing that'll change is that if your a value is greater than 1, you'll have an increasing graph. And if your a value is between 0 and 1, you will have a decreasing graph. Now, there's these little notes down here that I said that I was going to mention on the previous page again. When we're talking about the base has to be greater than 0. You'll notice here we had a is greater than 0 but less than 1, and we had a is greater than 1. That's all of these being greater than 0. The reason why is that you actually can't graph something with a negative base. Think about what this would look like. So if you have a negative base, in fact, let me just see if I can open Desmos for you. Okay, so just pause the video so you didn't have to see me setting this up. But here I've put in y equals negative 1 to the x, and look what the graph looks like. It's dots. Because what's happening? Well, when I put in x is 0, I get negative 1 to the 0 is 1. Okay, I get a dot. That one's a dot. Then when I put in x is 1, I get a y value of negative 1. And then when I put in x is 2, I get a y value of negative 1 squared, which is 1. And then it's going to kind of flip-flop in between. And in fact, it just confuses Desmos. I mean, this isn't even that complicated of a one. If you think about it, every other exponent would make the base even, or sorry, positive or negative. So we'd go 0, 1, and then we'd go negative 1, and then we'd go when x, oh, there it is there. When x is 2, we would have positive 1, and it would go back and forth. And so if you think about it, it'd be like this jagged graph that would just kind of go back and forth to negative 1 and positive 1. But the moral of the story is it is not an exponential function. It is not following this exponential growth or decay pattern. So your a value has to be greater than 0. It cannot be negative. And the other thing is that a cannot equal 1. If you put in a base of 1, 1 to any exponent is just 1. So it would actually be a constant function. It wouldn't be an exponential function. Okay, that is the end of the first video for 5.2.